Hello, we are Group 8 and we have analyzed Uber's search price algorithm, how Uber uses big data technologies to implement dynamic pricing in their platform. Uber is a data-centric company. Every decision of the company is data-driven and essential to optimize their services. The search algorithm allows Uber to optimize resource allocation and maximize profit. Uber is able to connect drivers and customers in a more efficient manner. On one hand, they incentivize drivers to work when and where they are needed the most, and on the other hand, customers get a ride when they need the most. This is a big data problem because it fulfills the 5 Bs. From volume, Uber's scope is enormous with 100 million riders and 5 million drivers, producing a total amount of nearly 19 million trips every day. Velocity, data is constantly being generated and is transmitted in real time as Uber operates in more than 900 cities. Variety, the data comes in all sorts of structures. And veracity, the data comes from many sources and formats, making the data quality one of Uber's big data challenges. And the value is inside the aggregated data and the impact it produces.
Okay, let's start with the big picture, and what is actually already interesting is that Uber refers to its big data lake as a unified serving layer which serves the entire company with information and processing power. And when we have a look at the technologies that are used for the search price algorithm, we can already see that there are some well-known open source frameworks within the Uber data lake, for example Kafka or Spark, but we can also see that Uber invented some technologies like Udemy or Michelangelo to accomplish Uber's business needs. What we can also see is that Uber uses a bunch of technologies that are referring to batch, to micro-batch, and also to streaming. But unfortunately, things are not that simple. On the right side, you can see actually the data flow and also the component interaction. And based on these two figures, we want to clarify how the Uber big data lake. So let's start with the data sources, and we would like to start with the new data, so data that isn't currently in any Uber database. And the main data sources for that are the Uber app, Google, and social media. When we have a look at the Uber app, we fetch session data, which is actually all the data that is gathered during a trip. And also we need the GPS data from the riders, but as well from the drivers. From Google, we need map data, which is considered as semi-structured and in a batch way, but also we need the traffic data, which is also semi-structured, but is streaming data, to better predict the estimated time of arrivals. From the social media, we need event data, which are, for example, concerts, which are semi-structured and batch to better forecast in the long run. And we also need activity data, which is considered as posts with a location tag, so we can see where the demand will increase soon. To act like a unified serving layer, the data within the serving layer needs to get back to the big data lake. We consider these data as historic data. Historic session data is stored in the Uber schema list database, and we consider them as semi-structured. And also rider and driver data, machine learning features, and machine learning models are semi-structured and stored in the Cassandra database. What is not quite obvious, but we need this for data ingestion.
In the ingestion layer, the search price algorithm creates both microbatch and stream ingestion into Uber's data lake using Kafka Connect. The snapshot processes in Uber's traditional ingestion solutions used to take from minutes to hours, which rapidly became inefficient for Uber's data size and operations, preventing this solution from being the most adequate for their architecture. So the need for a new solution with fresher and faster insights led them to develop DB Events, their own data lake integration solution. The first step of DB Events is about ensuring the quality and efficiency of data. This led them to develop an in-house schema management tool which ensures that every dataset, regardless of its source, follows a custom implementation for ingesting the data into Kafka. So within this DB events, within the schema management, we have two different examples. On one hand, Uber developed an open source solution called Storage Tapper, which carries pre-ingestion tasks for schema-less data. It encodes the events and the logs in Apache Arrow format, schematizing this data and polishing it later on in Apache Kafka. On the other hand, Cassandra data is pulled through an Apache Cassandra feature, a CDC, which is a change data capture system, which unifies the format in Apache Avro as well. So when the data has been standardized and the proper schema is applied, Uber's second step of DB events comes with Marmaray. Marmaray is Uber's own developed data ingestion dispersal framework, and it provides really good functionalities that maximizes Uber's data ingestion. It is capable of producing quality schematized data, and it ingests data from multiple data sources into Uber's data lake. In the storage layer, Uber relies on Apache Kafka for streaming data and Hadoop HDFS for batch data. Again, velocity here is a key for Uber, and the latency for new data is always been a big concern. Uber's traditional storage layer and solutions had high latency, which we'll talk over one day, which it was really far from Uber business needs. So the limitations here push them to create a new solution called the Hoodie library. It's a handy layer on top of HDFS that facilitates absurd and delete operations for historical data, allowing them to produce incremental ingestion and reducing the latency to less than an hour.
When it comes to data processing, batch processing is mainly used to keep the data lake updated, and stream processing is used for analytics. Actually, the packages Marmory and Hoodie are Spark packages, which means that Spark and Hive are already used during the data ingestion, but also Hive and Spark are used to duplicate tables, which means the incoming raw data gets separated in incremental mode and lattice mode table to serve different use cases. When it comes to streaming, this is mainly used for analytics, for example, up-to-date pricing, driver dispatching, or fraud analysis. Here, we rely on a Kappa architecture on fetching data from Kafka, and in general, Uber tries to shift its architecture to a Kappa architecture to only use stream processing within its pipeline.
Uber's data serving layer relies on Schemaless and Cassandra as its two data stores that focus on scalability, agility, and low latency. Uber actually created Schemaless as its own scalable data store to fit its needs. And for example, it allows them to save any JSON data without enforcing schema validation. It is a great solution for the price algorithm, providing real-time analytics and streaming data. Michelangelo and RSDB are tools to enhance machine learning and analytics. RS preloads data to allow real-time analytics, and Michelangelo acts like an entire serving layer for data scientists. We provide more information in our report. When it comes to Uber's overall architecture, it is important to highlight that Uber is focusing on shifting towards a Kappa architecture, which runs in the cloud. They do so because they need to integrate different pipelines, and Kappa allows them to have a unified code base between batch and streaming pipelines, as well as tolerate common problems such as delays. Kappa, in fact, allows them to account for late arriving and out-of-order events, such as when a rider waits to rate a driver until their next Uber session. Once again, after experimenting with common techniques, they ended up modeling their own Hive connector and switched it instead of the Kafka connector as a way to preserve the original streaming job state windows and triggers and facilitate backfilling with the correct order and ensure data quality at the same time. Given the scope and scale of Uber, the company needs to rely on a cloud infrastructure as they need an efficient, resilient, and scalable foundation. They are using AWS, and we assume they are relying on an infrastructure as a service type of agreement, as this allows for flexibility and scalability and allows them to use their services on demand and on a pay-as-you-go basis, eliminating the need for upfront capital expenses and for owning infrastructure. To conclude, our main takeaway is that a successful big data architecture can bring tremendous business value. As we can see in this graph, Uber's revenue increased dramatically. Anticipating user demand and shifting demand in real time is something that is almost unprecedented and wouldn't be able without big data. And it allows them to optimize operations planning, budgeting, detecting anomalies, and ultimately increasing revenues. The next takeaway is that by looking at a real company, we also realized how complex and integrate creating a big data architecture is. It is key to keep iterating and improving the architecture to reflect the most current business needs and growth. As well as we saw, customization is key to success, as there is no one way to use technology, and one solution might work well for one company but not the other. Thanks a lot.